3.3 Lesson 1, Derivative Functions, Numerically and Graphically. Objectives. 1. Given a function f, you'll be able to sketch the graph of f and f prime, which is the derivative of the function f, on a graphing utility. And objective 2, you will understand the relationship between the graph of f and its derivative. In the previous lesson, we looked at the definition of the derivative of a function at a point. The derivative of a function at a point is defined as the limit as x approaches c of this difference quotient. And the difference quotient gives us, in the context of a word problem, an average rate of change. Graphically, it gives us the slope of a secant line passing through 2 points, c f of c and x f of x. And when you take the limit of this difference quotient as x approaches c, you're moving the second point closer to the first point, and this limit is, by definition, the derivative of the function f at x is equal to c. In the context of a word problem, it would give us the instantaneous rate of change of the dependent quantity with respect to the independent quantity. And graphically, this derivative would give us the slope of the tangent line to the graph of f at x is equal to c. So how will we do objective 1 today? You'll be given a function f, so we will begin by looking at the function f of x is equal to x squared. And then our second example will be the function f of x is equal to x cubed. So we'll look at 2 examples today. So for the first example, we begin with the function f, which is f of x is equal to x squared, and we would like to sketch the graph of the derivative of this function, and we will do this numerically. What that means is we will find the derivative of the function f at several values of x, such as -2, -1, 0, x is equal to 1, and x is equal to 2. And how will we find each of these derivatives? By using the definition of the derivative of a function at a point that we learned in the previous lesson. When we do this, we say we are finding the derivative function numerically by calculating the derivative of the function f at particular values of x using this definition. So in objective 1, we would like to sketch the graph of f, which is very easy. The graph of f of x is equal to x squared is just a parabola. And we'd like to also sketch the graph of the derivative of this function by calculating the derivative numerically for several values of x using this definition from yesterday. And of course, I will also show you how you can sketch the graph of f prime on a graphing utility, but we'd like to first do this by hand so you understand what we mean by the numerical derivative, and you will also understand objective 2, the relationship between the graphs of f and f prime. So for the function f of x is equal to x squared, we'd like to find each of these derivatives of f at these values of x, and we will do that by using the definition of the derivative of a function at a point. So here is the definition of the derivative of a function at a point. Our function is f of x is equal to x squared, and we'd like to find f prime evaluated at -2, -1, 0, 1, and 2. So if you look at my work here, I need to have the limit as x approaches c of this difference quotient, and my difference quotient has f of x, which is just x squared. So in my first example, I have the limit as x approaches -2 of f of x minus f of c. So what is f of c? In this particular example, c is -2. So f of c would be the function f evaluated at x is equal to -2. -2 squared is 4, so I have minus 4 divided by x minus c. Minus c in our example here, c is -2, so minus -2 is plus 2. So we get that from the definition of the derivative of a function f at a point. And then we have a difference of 2 squares here, so we can factor the numerator as x plus 2 times x minus 2. And then we're able to cancel the common factor of x plus 2, and we're left with the limit as x approaches c, which is -2, of x minus 2. The function y is equal to x minus 2 is continuous on the real line, and because it's a continuous function, the limit of the function as x approaches c will be equal to f of c, and you can do what we call direct substitution. Substitute -2 for x, and -2 minus 2 is -4. In the same way, you're able to use this definition of the derivative of a function f at a point to calculate the derivative of the function f at x is equal to -1 and at x is equal to 0. F prime of -1 is -2. F prime of 0 is 0, and you can check my work. And we will also take a look at the derivative of f at x is equal to 1 and 2. And you can see that the derivative of the function f at x is equal to 1 is equal to 2, and the derivative of the function f at x is equal to 2 is equal to 4. So from the work that we just did, we're able to calculate numerically the values of the derivative of f at these values of x. So the derivative of the function f at x is equal to -2 is -4. The derivative of f at x is equal to -1 is -2. The derivative of f at x is equal to 0 is 0. The derivative of f at x is equal to 1 is 2. And the derivative of f at x is equal to 2 is 4. So remember, the derivative, as we learned yesterday, tells us the slope of the tangent line to the graph of f at these x values. So what that means is the slope of the tangent line to the graph of f at x is equal to -2 is -4. The slope of the tangent line to the graph of f at x is equal to -1 is -2, and so on. With this information, we'd like to sketch the graph of f, which is f of x is equal to x squared, and we'd like to use what information we have here about values of the derivative function at these x values to plot these 5 points, and these 5 points will be on the graph of the derivative function. And then we would like to understand the relationship between the graphs of f and f prime. So here we have the graph of f of x is equal to x squared. And to get the graph of f prime of x, I need to plot these 5 points. So I can plot 0, 0, I can plot 1, 2, and I can plot 2, 4 here. -1, -2, it's a little bit beyond my window. And then I have -2, -4, which would be below the screen. And if you look at these 4 points that I'm able to get on my screen here, and if I were to connect them, I get this line. And this would be the graph of the derivative. This would be the graph of f prime. And here we have the graph of f. You can also do what we just did with graphing f prime of x using a graphing utility such as Desmos. To do it using Desmos, here's what you would do. You would enter your function f of x first, and you would get the graph of f of x, which is the parabola that you see here. And then to graph the derivative of the function f, you can enter the keystrokes d, the division symbol, dx. This is read the derivative with respect to x of the function f of x. And then Desmos will do this work for you. It has its own algorithm for doing it. It may not do it exactly the way you saw me do it. It has its own programming. It may approximate these values to a great degree of accuracy using what we call a symmetric difference quotient or something like that, and it will give you the graph of f prime. We would like to discuss the relationship between the graph of f and its derivative. And to help us understand this relationship, you need to go back to understanding that the derivative tells us slopes of tangent lines to the graph of f at particular x values. So for example, at x is equal to 0, the tangent line to the graph of f is horizontal. And the slope of that tangent line is 0, and that's why f prime is 0. Now prior to x is equal to 0, you can see that the tangent lines to the graph of f are downward sloping. For example, this tangent line to the graph of f at x is equal to -2 has a slope of -4. So when you have tangent lines that are downward sloping, their slopes will be negative values. And when do you have tangent lines that are downward sloping? You have tangent lines that are downward sloping when the original function f is decreasing. So when the original function f is decreasing, the graph of f will have downward sloping tangent lines which have negative slopes, and therefore the derivative of the function f will be negative on intervals of x where the original function is decreasing. If you look at x is equal to +2, you can see that f prime is equal to 4. Again, the derivative tells us the slope of the tangent line to the graph of f at x is equal to 2. Because the slope of the tangent line is positive, you can see how that relates to the graph of f. So whenever you have the graph of f rising from left to right, in other words, the function f is increasing, the tangent lines to the graph of f, where the function f is increasing, will be upward sloping and will have positive slopes. And therefore, the derivative of the function f will have positive values. So the main observation you should make is that when the original function f, when the function f is decreasing, the tangent lines have negative slopes and the derivative will be negative. You can see that the graph of f prime is below the x-axis. It has negative values. When the tangent line to the graph of f is horizontal, its slope is 0, so the derivative is 0, and you can see that the graph of f prime has an x-intercept, and when the function f is increasing, the tangent lines will have positive slopes, and therefore the derivative will be positive. So we just looked at objective 2. You will understand the relationship between the graphs of f and f prime, and that has to do with what the derivative represents. It represents slopes of the tangent line to the graph of f at certain values of x. So we understood that when the function f is decreasing, the tangent lines will have negative slopes, and therefore the derivative will be negative. When the function f is increasing, the tangent lines will have positive slopes, and therefore f prime will be positive. And prior to that, we looked at objective 1. Given a function f, you will be able to sketch the graph of f and its derivative on a graphing utility. We will do the same two objectives with the second example. Our second example will be the function f of x is equal to x cubed. So given f of x is equal to x cubed, you'll be able to sketch the graph of f of x and its derivative on a graphing utility. And we will do that numerically by calculating f prime of negative 2, f prime of negative 1, f prime of 0, f prime of 1, and f prime of 2 by using the definition of the derivative of a function at a point that we learned in our previous lesson. And that will allow us to plot points on the graph of f prime so that we can sketch the graph of f prime. So given a function f, you'll be able to sketch the graph of f and f prime, and we will do that by hand first, and we will see how we can do this using Desmos. And like we did for the previous example, we will also understand the relationship between the graph of f and its derivative. So here's what we need to do. Given f of x is equal to x cubed, we'd like to find f prime of negative 2, f prime of negative 1, and so on. And to do that, we'll be using the definition of the derivative of a function at a point. So our function f of x is x cubed, and we'd like to begin by finding the derivative of f at x is equal to negative 2 by using the definition of the derivative of a function at a point. So our c value in this example would be negative 2, so x is approaching negative 2, and we take the limit of the difference quotient as x approaches negative 2, and the difference quotient is f of x, which is, of course, x cubed, minus f of c. F of negative 2 would be negative 2 cubed, which is negative 8, minus negative 8 would be plus 8, and then in the denominator we have x minus c, and c is negative 2, minus negative 2 is plus 2. You can factor x cubed plus 8 by using the sum of two cubes factoring pattern. And when you factor the numerator using the sum of two cubes factoring pattern, you get x plus 2 because 8 is 2 cubed. So we have x cubed plus 2 cubed. So we have x plus 2 times x squared minus 2x plus 2 squared, which is 4, divided by x plus 2. You can cancel the common factor of x plus 2, and you have the limit as x approaches negative 2 of x squared minus 2x plus 4. And because this is a continuous function on its domain, the limit of the continuous function as x approaches negative 2 will be equal to the function evaluated at negative 2. So you can evaluate this limit by using what we call direct substitution. Substitute negative 2 for x, and you get 12. So f prime of negative 2 is 12. In a similar way, using this definition, you can find f prime of negative 1 to be 3, f prime of 0 to be 0, f prime of 1 to be 3, and f prime of 2 to be 12. So from the work that we did, we have this information about the derivative of f of x is equal to x cubed, evaluated at these values of x. So the derivative of f of x is equal to x cubed, evaluated at x is equal to negative 2 is 12. The derivative of f of x is equal to x cubed, evaluated at x is equal to negative 1 is 3. And we were able to find those definitions, we were able to find these values by using the definition of the derivative of a function f at a point, and we call this numerically calculating the values of the derivative of f at certain x values. So in objective 1, given a function f, you will be able to sketch the graph of f, which is easy to do, and we will use this information because now we have 5 ordered pairs that are on the graph of the derivative. So we will use these 5 ordered pairs to graph the derivative function. So here we have the graph of f of x is equal to x cubed, and we will get the graph of the derivative of f by plotting these 5 points that we know are on the graph of the derivative function. So we have negative 2, 12. We have negative 1, 3. We have 0, 0. We have 1, 3. And we have 2, 12. So we have these 5 points, and when we try to connect them with the smooth curve to get the graph of the derivative of f, we get this graph. So it appears to be a parabola, and that's the graph of f prime. So we've just done objective 1 for our second problem, where our function f was f of x is equal to x cubed. So we looked at the graph of f, and we also looked at the graph of f prime. First we did it by hand by calculating values of f prime for x is equal to negative 2, negative 1, 0, 1, and 2, finding the values of the derivatives, plotting the ordered pairs, and getting the graph of f prime. And then we looked at using Desmos to get the graph of f and f prime. We've done objective 2 for our first example, and now we will go ahead and do objective 2 for our second example. Understand the relationship between the graphs of f and f prime. To understand that relationship, remember that f prime is the derivative, and it gives us slopes of tangent lines to the graph of f at different x values. When we look at the graph of f of x is equal to x cubed, we see that at x is equal to 0, the graph of f has a horizontal tangent line. So the slope of the horizontal tangent line will be 0, so f prime evaluated at x is equal to 0 will be 0. And you see that here in our table. Now, before x is equal to 0, when we have negative x values, we can see that the graph of f has tangent lines with positive slopes. So for example, at x is equal to negative 2, the tangent line has a slope of positive 12. And at x is equal to negative 1, the tangent line has a slope of positive 3. When you look at the graph of f for x values that are less than 0, you can see that the graph is rising from left to right, which means the function f is increasing on the interval from negative infinity to 0. And when the function is increasing, the graph will have tangent lines with positive slopes, and therefore the derivative of the function will be positive. And that is why you see values of the derivative being positive for x values that are negative. And therefore the graph of the derivative function, since it has positive values, the graph will be above the x-axis. At x is equal to 0, the derivative is equal to 0, as we discussed earlier, because the tangent line is a horizontal tangent line. And the derivative would be 0, and the graph of the derivative will have an x-intercept. At x is equal to 1, the derivative is 3. The graph of f has a tangent line with a slope of positive 3. And at x is equal to 2, the derivative is 12. The graph of f has a tangent line with a slope of 12 at x is equal to 2. When you look at the graph of f on the interval from 0 to infinity for x values that are greater than 0, you can see that the graph of f is rising from left to right. The function f is increasing on this interval. And because the function is increasing on that interval, the graph of f will have tangent lines with positive slopes. It will have tangent lines that are upward sloping with positive slopes. And because the tangent lines have positive slopes, the derivatives will be positive. And that is why f prime is positive on this interval of x values, because the function f is increasing on that interval of x values. And because f prime is positive, the graph of f prime is above the x-axis. So to generalize, when the function f is increasing on an interval, its derivative will be positive on that interval. And we see on the interval from negative infinity to 0 that the function f is increasing. And we see that on the interval from x is equal to 0 to infinity that the function f is increasing. So on those two intervals, the function f is increasing and the derivative of the function f is positive. So the graph of the derivative function is above the x-axis. At x is equal to 0, the graph of the function f has a horizontal tangent line. The slope of the horizontal tangent line is 0, and the graph of the derivative function has an x-intercept. With our first example, the function f of x is equal to x squared was decreasing on the interval from negative infinity to 0. You can see that the graph was falling from left to right. And its derivative was negative for these values of x. And the graph of the derivative was below the x-axis. For the function f of x is equal to x squared, you can see from the graph of f that the function is increasing on the interval from 0 to infinity. The graph is rising from left to right for these values of x. And because the function was increasing on that interval, its derivative was positive on that interval. And you can see that the graph of the function f prime is above the horizontal axis because f prime is positive on that interval. And you can see that at x is equal to 0, the graph of f has a horizontal tangent line, the slope of which is 0, so the derivative is equal to 0 at x is equal to 0, and the graph of the derivative has an x-intercept there. So today we looked at these two objectives. Given a function f, you'll be able to sketch the graph of f and f prime, its derivative, on a graphing utility. You'll understand the relationship between the graphs of f and f prime. Important for you to understand is that the derivative of a function gives you slopes of tangent lines to the graph of the function at particular x values. And if in the context of a word problem, the derivative of a function gives you an instantaneous rate of change.